Good morning, everybody. I first want to thank the organizers for giving me the opportunity to participate this week. This is the first time I've attended Q2B, and I'm looking forward to really productive and informative next couple days. Let's see here. So let me go back. So I'm a physicist in the Quantum Information Sciences branch at the Air Force Research Laboratory Information Directorate, which we also colloquially call Rome Lab. And throughout this talk, or as the title suggests, I'm going to give an overview of the efforts of the quantum team at Rome Lab to develop heterogeneous, the building blocks of a heterogeneous quantum network. And so I just want to note in this context, when I say heterogeneous, what I'm referring to is a communication network within which different types of quantum systems, whether superconducting or trapped ion or photonic systems, are interfaced together and integrated in the hardware nodes to provide greater functionality, enhanced versatility, and ultimately a wider range of applications than if you had a single network with a single modality. And so hopefully that'll become clear what I mean by this as the talk goes on. But if you take nothing else away from this talk, what I hope to convey to you is that one of the overarching objectives of the quantum team at Rome Lab is to develop a quantum networking testbed to explore entanglement distribution and ultimately explore the use of entanglement distribution for Air Force applications. Okay, so with that, I'll start off by giving a quick outline of the rest of my talk. So initially, I'll give a 30,000-foot single slide snapshot of the Air Force Research Lab Information Directorate, just to provide some context of how this work, the quantum team, fits into AFRL's mission. This will segue then into, again, a brief discussion of the Air Force's broader interests in quantum information science. And again, I'm not going to dive too deep here. And in fact, there will be another talk tomorrow given by Dr. Mike Haydick, who is the Deputy Director of AFRL Information Directorate, also my boss. And he will discuss in more detail the broader efforts in quantum information science across all the Air Force Research Laboratory Directorates. So please check that out if you'd like to learn more details about the full scope of AFRL's quantum program. I'll then spend the remainder of the talk discussing the quantum team's effort at Rome to develop heterogeneous networking hardware. And so I'll outline some of the major research thrusts, as well as highlight some recent developments toward developing the interconnects between different qubit modalities. And then if I have time, I'll chart some future directions. Okay, so the Rome Lab, the Information Directorate. For those of you who aren't familiar with Rome, it's located smack dab in the middle of New York State. It's just south of the Adirondacks, a couple hours east or west of Albany, a couple hours east of Rochester. The actual directorate sits on the site of an old Strategic Air Command B-52 base and that relocated back in the 1990s. But you can still see vestiges of that base today, including, if you look in the picture on the left here, on the right side, you'll see this large blue structure. It was a former hangar for aircraft, including P-52s. And that hangar has been repurposed and refurbished in recent years to house a state-of-the-art open research facility for various topics in high tech, including quantum. And I'll try to say more about that facility a little later in the talk, but it's known as the Innovari Advancement Center. So research at the Information Directorate at Rome Lab, it spans the gamut of what you would expect in information science that's relevant to the warfighter. So command and control, communications, computing, intelligence, and cyber, so C4I+1. And the specific research topics span the range from high-performance computing, machine learning, to data fusion, autonomous systems, resilient hardware, and of course, quantum. And the quantum research at Rome Lab pretty much falls within the domain of communications and computing. Okay, so I don't think I have to convince anybody here that quantum systems, quantum technologies have the potential, underscore the word potential here, to catalyze transformative advancements in how we collect, process, and communicate information. And so the Air Force is motivated in cultivating those advancements for strategic and tactical, multi-domain capabilities in 4 broad technology applications. So timing, sensing, computing, and networking. And so, across these domains here, a lot of the research is at the lower TRL, technology readiness level. And in fact, a lot of it is basic research. But as we heard a little bit about earlier today, and you'll hear more about in Dr. Haydick's talk tomorrow, in the domain of timing and sensing, we're beginning to see quantum technologies for Air Force applications begin to be field tested. And so, for example, and again, this was brought up earlier in an earlier talk this morning, tactical atomic clocks. So atomic clocks where the size, weight, and power of the swap is being reduced. They're being more robust for operation outside of the laboratory. And all of that is being engineered while maintaining the frequency stability, timing stability that's sufficient to enable navigation and time transfer, synchronization, ultimately the goal to be in GPS denied environments. So that's one application where quantum-enabled, quantum-enhanced technologies are starting to be tested for real-world Air Force applications. Another great example are cold atom clouds, interferometers, which are being developed as sensors of magnetic fields, or gravimeters for sensing gravitational anomalies like tunnels and bunkers underground. So some of the first examples of quantum-enabled, quantum-enhanced technology being field tested and applications of relevance to the Air Force would be under self-sustained PNT, so positioning, navigation, and timing. With respect to computing and quantum networking, applications of technology to actual Air Force applications are further out on the horizon, but under computing, for example, there are active efforts, including at Rome Labs and also in other DoD laboratories, for exploring the use of NISC-era quantum processors for problems like logistics, optimizations, also for simulation of complex systems for material synthesis and chemical reaction type problems. And under quantum communication and quantum networking, applications there of quantum technology for Air Force relevance are even further out on the horizon. But as I'll try to convey today, there's extensive effort in developing technology to push the state of the art in quantum networking, to extend entanglement distribution beyond the state of the art of 3 or 4 nodes, and starting to understand how we can further improve our control of entanglement and entanglement distribution, and what applications we can apply that to for Air Force operations beyond some of the ones that are typically cited, like secure communications and entangled sensor networks and so forth. So I've said a little bit earlier that at the Information Directorate, quantum information research is focused primarily on computing and networking. And so let me just give you the breakdown of that. You can think of the research that's going on at Rome Lab in quantum to be broken up into 3 broad categories. You'll notice I only have 2 of those categories out there. Regrettably, I omitted one of them, which I'll highlight what that is in a second. But you can categorize the research at Rome Lab in quantum to fall under quantum software or algorithms development, quantum hardware effort, and the group that I left out was the theory group and quantum information processing. And so for most of the talk, I'm going to focus on the hardware effort, most of the rest of the talk, but I just want to highlight the activities under the algorithms effort and also the theory effort. So the quantum algorithms team is led by Laura Wessing, who's at the conference this week, so you can certainly talk to her for more details about that group's activities. But what the quantum algorithms team focuses on is developing and maintaining expertise on commercial quantum processors, and at the same time identifying Air Force challenges, Air Force problems for which to develop quantum algorithms to provide advantages and solutions to those problems, in particular as the commercial quantum processors become more and more powerful. And I should note that the software team has access to a couple different commercial cloud-based quantum processors, both IBM and IonQ. And in fact, the information directorate is an IBM quantum hub, which enables partners with the Air Force Research Lab, Information Directorate, in industry, academia, and government to also access those cloud-based systems. The quantum theory effort is led by Paul Alsing, and they have deep expertise in theory of information processing with photons, expertise in quantum optics, and also the characterization of entanglement in high-dimensional systems. And finally, the hardware effort is multifaceted. We have a trapped ion group that was founded by Kathy Ann Soderberg. And I want to note that Kathy Ann recently was appointed to be the first Air Force ST in quantum. And so she's now working at the senior executive service level to help formulate Air Force policy across the broader Air Force. But her team still marches on into developing trapped ion systems at the lab. The integrated quantum photonics team is probably the most mature experimental quantum effort at Rome Lab. It's led by Mike Fanto, and it goes back to about over 10 years now. And finally, there's the superconducting qubit effort, which I lead. I'm the technical lead for that. That began about 4.5 years ago when I joined AFRL. So I just want to note all of this work here involves around 20 government civilian researchers, most of them PhDs. We also have a comparable number of contractors working with us on this effort. And I should note that all this work is overseen by our branch chief, Dr. Don Teleska, who is also here this week, whom you can talk to for more information about the branch. Okay, so for the rest of the talk, I'm going to focus on one particular objective here. I want to back up and say each of these hardware efforts has multiple projects trying to push the state of the art of those different qubit modalities. But one of the overarching objectives of our branch, the Quantum Information Sciences branch, is to develop the interconnects between these different qubit modalities. And the motivation for this can simply be understood that different qubit modalities have different functionality, they have different characteristics, different respective favorable attributes, which you could draw from to tailor hardware for a particular functionality, right? So to give a simple example, photons, particularly in the telecom domain, can be transmitted with low loss through optical fiber and through the atmosphere, and so they're natural, flying qubits, the carriers of quantum information, and can be utilized to establish entanglement between network nodes to establish, quantum channels for further operations. By contrast, trapped ion systems, they have some of the longest coherence times of any quantum system and technology out there, and so they're natural memory qubits. And then, of course, superconducting systems, they're macroscopic circuits that you can strongly couple to and that you can strongly couple together. So you can engineer relatively fast, 2-qubit gate logic operations, and you can engineer essentially deterministic entangling operations. Whereas with, so for example, trapped ion systems, their gates are an order of magnitude slower, and entangling operations are generally probabilistic. And so this illustration here is just an oversimplified example of how these different qubit technologies could give you different functionality in hardware. The broader point I want to make is that to scale up to networks of greater complexity in topology and number of nodes and scaling over greater length scales, I think will require developing these interconnects so that we can utilize these different technologies with their different functionalities to support that kind of increased complexity, for more versatile, more diverse range of applications in the future. So what I'll do, I think I have about 5 minutes left or so. What I want to do is just go through and give some examples of the different yellow arrows here, the different interconnects that we're developing at Rome Lab for the different groups. So I'll start with the ion photonic interface work. And so just to start off, the photonics team at Rome has done a tremendous amount of work developing, along with collaborators in industry, academia, and AIM Photonics, American Institute of Manufacturing, their foundry in Albany. They've done a tremendous amount of work developing a 300 millimeter silicon-based platform for integrated quantum photonic circuits. And so they're really pushing the state of the art in demonstrating low loss photonic waveguides and different materials, low loss, wide bandgap materials and electro-optic materials, or nonlinear materials for efficient entangled photon pair generation. Also, tackling the problem of developing robust and efficient sample packaging, including I/O. And importantly, this picture up here is a wafer from several fab runs ago, a couple years ago, so it's an older generation device. But on this wafer, there's arrays of all the components you need for processing light on chip, from beam splitters to Mach-Zehnder interferometers to photodetectors, photon sources, as I said before, but importantly, also elements for interconverting or transducing to other modalities like ions and superconducting systems. And so one example of that are electro-optic wavelength converters. They've developed devices on chip to convert over multiple wavelength domains, from infrared to visible to ultraviolet. And so why it's important to be able to convert from infrared to visible to ultraviolet is if you have a photonic photonic processor working efficiently in the infrared domain, and you'd want to, say, output entangled pairs of photons to trapped ion systems. Generally speaking, some of the best memory, best ions for memory and for processing, they operate at wavelengths in the visible and even UV. So what they're doing is they're developing elements on chip to convert between various wavelengths that would enable interfacing with different species of trapped ion systems. Another great example from collaborative work done between the trapped ion team and the photonics team is the development of multi-channel waveguide photon splitter. And so an example of that's shown here, where there's an 8-channel photon splitter that can operate. They have designs for multiple wavelengths that are relevant to barium ion, which barium is important because it's a very good memory qubit. Also can be used for establishing remote entanglement. But what you can see here is the pitch of that waveguide splitter. It's been designed to match the pitch of the ions that are in the black and white here in a linear trap. And so you can, 1 minute, okay, thank you. So you can use this splitter to excite and extract light from those atoms there to control and measure them. And this will be important for remote entanglement. So running out of time, but I just want to highlight really quick the other interfaces work that's going on in the group, including the superconducting effort, so integrating superconducting with photonic systems and superconducting with trapped ion systems. And so this work is multifaceted, and really the overarching objective of this is to develop cryogenic ion trap hardware that integrates these different modalities together. And so what I want to say, for the first part of this, we're developing a modular superconducting qubit platform, which incorporates efficient tunable couplers for turning on and off gate operations between qubits, waveguides for mediating entanglement, distributing entanglement, metamaterial waveguides also for generating complex entangled states, and many, many more projects in support of developing this modular architecture. And for this work, it's really been critical that we've partnered with Rigetti Computing. For the past, since 2021, we've been contracting with Rigetti's Quantum Foundry. For them, we basically design our circuits that we need for this architecture and then submit the designs to Rigetti's fab, where they fabricate them, integrate high coherent superconducting qubits with our custom circuitry, and which is enabling now in the sort of newest generation devices for us to actually start to explore these new qubit coupler designs and waveguide architectures that we need to get to this scalable architecture. I'll just say as the last point, the two other directions here, we have efforts developing bidirectional microwave to optical connection so that we can develop photonic interconnects between cryogenic nodes and also to directly interconnect with photonic circuitry. And the very last thing I'll say is we're developing in collaboration with the trapped ion team, interfaces between superconducting and trapped ion architectures, testing the ion trap hardware at millikelvin temperatures. We've actually also contracted with Maybell Quantum Industries to develop a fridge that will facilitate the operation of a trapped ion at millikelvin temperatures, co-located and operated with a superconducting system. So with that, I appreciate your patience as I went over time there. I will just wrap it up by saying we have what I said in the beginning of that blue hangar that was converted into an open research center that is known as the Innovare Advancement Research Center. It's a basic research laboratory, so it has less stringent security restrictions, so we can have a wider range of colleagues work with us there, including foreign nationals. And that is something that just opened up in the last year and is a really exciting development for us. So if you have any questions, I'll be around all week. Please feel free to stop by and talk. Thank you for your time.